Welcome back to the Deep End, everyone. It is Wednesday, February 18th, 2026. You are listening to The Deep Dive.
It's good to be back.
And today we are doing something a little different. We're going to be looking at what feels like the source code of invention itself. We're talking about TRIZ. Now, before you hear that acronym and your eyes sort of glaze over, I want you to reframe this. This isn't just about, dusty old engineering manuals.
No, not at all. This is about the fundamental logic of how you solve a contradiction. It's really about the physics of problem solving.
Right.
How do you get A without losing B?
Right. And before we get into the gears and the code, I have to give a massive shout out to the team that literally powered this deep dive.
Absolutely.
This entire exploration is brought to you by @IdeaMechanics9 on YouTube. And look, if you're listening to this, you are probably the type of person who just wants to know how things work.
You're curious.
You're curious. Well, @IdeaMechanics9 is basically the visual encyclopedia for that exact curiosity.
We talk a lot about those aha or eureka moments on this show, but the whole philosophy over at Idea Mechanics 9 is a bit more rigorous.
A bit more structured.
Exactly. Their whole stance is that innovation is a repeatable process. It is not some random lightning strike. It's a system, a method that you can actually learn.
Which is a pretty bold claim, honestly. Most people I know think of creativity as this mystical, ephemeral thing you can't bottle.
Right, that it just happens to you.
Yeah. But if you watch their channel, they make a really compelling case that you can, in fact, systematize genius.
They break it down into tools and principles, just like we're about to do.
So do us a favor, and do yourself a favor. Pause this for a second, open up YouTube, and go subscribe to @IdeaMechanics9. While you're there, check the links in our description. They've curated some seriously powerful innovation tools.
And please leave a comment on their videos, on ours, wherever. Let us know what you think about this whole idea. Is innovation a repeatable process?
Yeah, we really want to hear your take. The inspiration versus algorithm debate is a fascinating one.
Absolutely. We should definitely have that conversation in the comments.
Okay, let's get into the meat of it. We are tackling the third batch of the TRIZ Inventive Principles today. We're covering principles 21 through 30.
The third set of 10.
For the people who might have missed our last few deep dives on this, can you give us the 30-second elevator pitch on TRIZ? Why does the Soviet-era engineering theory still matter to someone sitting in traffic with an iPhone in 2026?
Because the fundamental problems haven't changed. Only the medium has. TRZ was developed by a guy named Genrich Altschuler, who painstakingly analyzed something like 40,000 patents.
40,000? That's a lot of reading.
It's an incredible amount of work, and he wasn't looking for what was invented. He was looking for the pattern of the solution, the how.
The underlying logic.
Exactly.
Yeah.
And he found that whether you're designing a jet engine or a coffee cup or a piece of software, there are only about 40 universal ways to solve a problem. These are the inventive principles.
So it's basically a cheat sheet for invention?
It's an algorithm for creativity.
Oh.
It's built on the assumption that someone, somewhere, has already solved your problem. They've just solved it in a completely different context.
And our mission today is to map these next 10 principles, 21 through 30, from the factory floor to the digital world we all live in now.
That's the plan, to show how the same logic that applies to a steam pipe also applies to your smartphone.
Okay, let's start with section 1, speed and perspective. This is going to cover principles 21 and 22. So principle 21 is officially called skipping or sometimes rushing through. Now, my first gut reaction is that rushing is bad. If I rush a project, I make mistakes, haste makes waste and all that.
In a linear process, you're absolutely right. But in the world of TRIZ, principle 21 is very specific. It's about resonance and hazardous exposure.
Okay, what does that mean?
It suggests that if a process has harmful side effects, things like heat or pain or chemical degradation, those effects usually take a certain amount of time to build up and do their damage.
They're not instantaneous.
Exactly. So if you can conduct the main process faster than the harm can propagate, you bypass the damage entirely. You're done before the negative consequence even gets started.
You're literally outrunning the consequence.
You're beating the physics of conduction.
Yeah.
And the most visceral, perfect example of this is at the dentist.
Oh, great. I was hoping we wouldn't have to go there, but okay, let's do it.
Think about the old days of dentistry. Those low-speed, belt-driven drills, they were pure torture.
I can almost hear it now.
And the problem wasn't just the vibration. It was the heat. Intense, focused friction heat.
Right, from the grinding.
Right. But it's specifically about something called thermal relaxation time. The tooth, your enamel, and the dentin underneath it conducts heat. If you drill slowly, that friction generates heat, and the heat has time to travel, to seep through the bone,
Oh, no.
and literally quick the pulp, which is in the nerve center of your tooth. That process is called necrosis. The nerve dies because it got too hot.
That is a genuinely horrific image. So the high-speed drill isn't about saving the dentist's time, it's about saving my nerve.
100%. Modern dental turbines spin at, what, 300,000 to 400,000 RPM? It's an incredible speed.
Unbelievable.
At that velocity, the little diamond burr cuts a tiny chip of enamel and ejects it before the heat from that cut can transfer from the chip to the rest of the tooth.
So the heat leaves with the dust.
The heat is carried away in the debris. You are literally moving faster than the rate of thermal conductivity in your own tooth.
Wow. So it's a race. The drill versus the laws of thermodynamics.
And the drill wins. And we see the exact same principle, the same logic, in LASIK eye surgery. The excimer laser doesn't burn your eye.
It's not a burn. It feels like it would be.
No, it uses a process called photoablation.
And ablation just means removal, right?
Vaporization,
Yeah.
essentially. But the absolute key is the pulse duration. The laser pulses are in the nanosecond range, a billionth of a second.
So incredibly fast flashes of light.
Unimaginably fast. If they were longer, say in the microsecond or millisecond range, the heat from the laser would dissipate into the surrounding corneal tissue. It would cause scarring thermal damage.
The very thing you're trying to avoid.
By rushing through with these nanosecond pulses, the laser breaks the molecular bonds in the tissue, and the tissue just vanishes into gas before the heat even realizes it's supposed to spread.
The side effect never gets the chance to happen. Okay, so in the physical world, speed prevents thermal damage. How does this map to the digital world? We don't really have friction in software, do we?
We don't have physical friction, but we have latency. And latency causes user churn, which I would argue is the digital equivalent of necrosis.
User necrosis, I like that. It's when the user's interest dies on the screen.
Exactly. Take a look at modern recommendation algorithms, TikTok, YouTube, Netflix. The harmful factor here is user boredom. It's a killer.
The thumb is always hovering over that swipe.
Always. If that system pauses for even 3 seconds to calculate the absolute perfect video for you, you're gone. You've already swiped away. The system has failed.
So it can't be perfect, it has to be fast.
It has to rush through petabytes of data using what are called approximate nearest neighbor algorithms. They intentionally trade a tiny, tiny bit of accuracy for a massive gain in speed.
All to avoid the harm of you closing the app.
Precisely. They are skipping the perfect calculation to save the engagement. They rush through the data processing to beat the decay rate of your attention span.
That's a great transition to Principle 22, Blessing in Disguise. This one sounds less like an engineering principle and more like a self-help book, turn lemons into lemonade.
It does sound a bit soft, doesn't it? But in engineering and in systems design, it's actually a ruthless efficiency principle.
How so?
It asks a very simple but profound question. Why am I spending resources to fight, eliminate, or contain this negative factor when I could potentially flip its vector and make it do useful work for me?
Don't just remove the bad thing, use it.
Put it on the payroll.
Okay, give me the big industrial heavyweight example of that.
Waste heat. It is the bane of almost every engineer's existence. The second law of thermodynamics dictates that every engine, every server farm, every factory generates heat as a byproduct.
It's unavoidable.
It's unavoidable.
Yeah.
And usually we build these massive cooling towers or refrigeration systems, spending energy and money and water just to throw that heat away into the atmosphere.
So we pay money to get rid of energy we just created.
Which is completely insane if you stop and think about it. Principle 22 says, stop fighting it. Use it. This is the entire basis of what's called cogeneration, or CHP, combined heat and power.
Right.
A power plant generates electricity, and instead of venting all that hot steam, it pipes that waste heat into a district heating system to warm 50,000 homes in a nearby city.
So the harmful byproduct, the heat, becomes a second sellable product.
It goes from being a liability on the balance sheet to an asset. It completely changes the economics of the system.
Okay, that's a great example. What about something more chemical?
The catalytic converter in your car. It's a perfect application of this.
I know it cleans the exhaust, but I never really thought about how. How is it a blessing in disguise?
Well, think about what the exhaust is. It's a stream of hot, fast-moving, and highly toxic gas. Carbon monoxide, nitrogen oxides, really nasty stuff.
The harmful factor.
The harmful factor, exactly. Now, a catalytic converter doesn't just filter it like a coffee filter. It uses the heat and the flow of the exhaust itself to activate the catalyst inside. usually platinum, palladium, rhodium.
So the heat from the engine is necessary for it to work.
It's essential. It uses the energy of the bad stream to power the chemical reaction that cleans it. It turns those toxic gases into much less harmful carbon dioxide, nitrogen, and water.
It literally uses the problem to power the solution.
It's a beautiful self-contained system. And there's a really cool modern example in the outline for today about 3D printing.
Yeah, I saw that. Surface roughness. Which is interesting because usually if I 3D print something, I want it to be as smooth as possible. Roughness is a defect, right?
For a consumer product like a phone case or a little figurine, yes, you want it smooth. But let's say you're an engineer designing a heat exchanger. Think of a car radiator or the heat sink on your computer CPU.
Okay.
To get heat to exchange efficiently from a solid to a gas, like from metal to air, you want turbulence. You want the air to get all mixed up as it flows over the surface. Smooth surfaces create something called laminar flow, where the air just kind of slips by in neat layers without grabbing much heat.
So a perfectly smooth surface is actually bad for cooling.
In that specific context, yes.
Hmm.
Now, one of the so-called defects of many 3D printing processes is that it creates objects layer by layer, which results in a slightly ridged or staircase effect on the surface. It's naturally a bit rough.
Right, you can feel the layers.
And engineers realize this roughness, this flaw, actually increases the surface area, and more importantly, it trips the airflow into that desirable turbulent state.
Which makes it cool better.
Significantly better. So they stopped trying to sand the parts smooth and started designing for that roughness. They deliberately oriented the parts in the printer to maximize that staircase effect where it would be most useful.
Wow. They turned a manufacturing limitation into a performance enhancement.
That's Principle 22 in a nutshell. And I think this maps really cleanly to data science too, especially with anomalies.
Right. The old way of thinking was if you have a data set and you see a weird spike or an outlier, you delete it.
Scrub the data. Oh, that's a glitch from the sensor. Let's just clean it up. Normalize the curve.
But Principle 22 says that the glitch is the signal.
Exactly. In predictive maintenance for a jet engine, that one weird vibration reading isn't a mistake. It's the first whisper that a bearing is going to fail in 500 hours.
And in credit card fraud detection.
The one transaction that doesn't fit your normal pattern, the purchase in a different country at 3 a.m., that isn't noise. That is the crime.
So don't scrub the stain, analyze it. The stain tells you where the leak is.
That's it perfectly. The flaw contains the most valuable information.
All right, let's move on. Section 2. Control and autonomy. We're looking at principles 23 and 25. Let's start with number 23, feedback.
This one, this is the backbone of all modern civilization. It's cybernetics. Feedback is simply the process of measuring your output and using that information to adjust your input.
It's the loop. Measure, compare, adjust.
It's the loop. And the absence of the loop is just as illustrative. Think of a cheap, old-fashioned toaster. That's an open loop system.
How so?
You put the bread in, you turn a dial for time, and it just heats up for that amount of time. It has no idea if the bread is frozen solid or if it's already slightly burnt. It just runs the timer and stops.
Which is precisely why my toast is never, ever right.
Exactly. A closed loop or a feedback system would have a sensor, maybe an optical one, that's actually watching the color of the bread. When it hits that perfect shade of golden brown, it pops up. That's feedback.
So this is happening constantly in the phone in my pocket.
Constantly. Probably the most critical one is something called thermal throttling. We've already talked about heat as a harmful factor.
Right.
Your phone's processor generates a massive amount of heat when you're doing something intensive like playing a high-end game. If it gets too hot, the silicon itself starts to degrade. The chip physically wears out faster.
So the phone has to monitor itself to prevent itself from cooking itself.
It uses something called a PID controller loop. It has a temperature sensor on the chip. It's constantly checking, am I over 90 degrees Celsius? If the answer is yes, the logic says, okay, cut the voltage to the CPU by 10%.
And then it checks again.
Immediately. Still too hot. Okay, throttle GPU, cut the screen's frame rate to 30 frames per second. It will actively and deliberately degrade your experience to save its own life.
And that's why my game starts to stutter when I'm playing outside on a hot day.
That's the feedback loop kicking in to prevent catastrophic hardware failure. We also see this in cars with their audio systems.
Oh, the volume thing that goes up when you speed up?
Speed-sensitive volume control. It's a simple, elegant feedback loop. There's a microphone in the car that's listening to the ambient road noise, the noise floor. As you accelerate and drive faster, the road noise and wind noise increase. The noise floor rises. The feedback loop detects this and boosts the gain on the amplifier just enough to maintain a consistent signal-to-noise ratio for your music.
It feels like magic, but it's just a simple piece of logic. If noise moves up by X, move volume up by Y.
And of course, the ultimate expression of this principle today is autonomous driving. A self-driving car is basically a rolling supercomputer managing thousands of simultaneous feedback loops.
Thousands.
Oh, absolutely. You've got Kalman filters processing data from LiDAR and radar and cameras. The system predicts where a pedestrian will be in the next tenth of a second. It measures where they actually are. It calculates the error between the prediction and reality, and then it adjusts the steering torque or the brake pressure,
Right.
all within milliseconds.
It's making thousands of these tiny micro corrections every single second.
It's the fundamental difference between guessing where you are and knowing where you are. That's what feedback gives you.
Now, let's actually jump ahead for a second to Principle 25, self-service, because it feels like the next logical step from feedback.
It is. It's a perfect follow-on.
If the system has feedback and knows what's going on, then let it take care of itself.
Right. Principle 25 is about designing a system to perform its own auxiliary functions. Things like maintenance, cleaning, repair, replenishment autonomously.
The classic example that always comes to mind is the self-cleaning oven.
It is. It's a process called pyrolysis. The oven locks itself, heats up to an insane 500 degrees Celsius or 900 Fahrenheit, and just carbonizes all the food residue into a fine white ash.
You don't scrub. The oven services itself. You just wipe out the dust at the end.
It removes the human from the maintenance loop. But the really cutting-edge stuff is happening in material science with things like self-healing circuits.
Okay, now this sounds like science fiction and probably very expensive. How does a circuit heal without a tiny little soldering iron?
It's all about clever chemistry. Imagine a polymer material, like the substrate of a circuit board, that's embedded with millions of tiny microcapsules. Think of them as microscopic bubbles filled with a liquid conductive monomer.
A liquid metal, almost.
Sort of, yeah. And it's just sitting there, inert. Now, when a microcrack forms in the circuit board, maybe from thermal expansion or physical stress, that crack tears open the microcapsules in its path.
Releasing the liquid.
The liquid flows into the crack via capillary action. There's also a catalyst agent embedded in the surrounding material. When the liquid hits the catalyst, it polymerizes. It hardens, physically and electrically bridging the gap.
So it's like the system has its own blood platelets, it forms a scab.
That is the exact biological analogy they use. It clots the wound to restore function. And this is absolutely critical for technology in inaccessible places, deep-sea cables, planetary rovers, or satellites. You can't just send a repair guy.
The system has to have its own immune response. That's
Yeah.
wild. Okay, let's circle back now into Section 3, bridging the gap. Let's talk about Principle 24, intermediary.
The intermediary principle is the great diplomat of TIZ. It's a very simple idea. If object A cannot or should not interact with object B directly, you introduce object C to act as a go-between.
It's the buffer, the
Yeah.
translator, the bridge.
All of the above. The outline gives a really specific and interesting robotics case study, an in-pipe inspection robot.
So a little robot that's designed to crawl through a sewer line or a water main.
Right, and you immediately run into a problem, a contradiction. You have an electric motor, which provides rotational energy. It spins,
Okay.
but you need the robot to crawl, which is a form of linear motion or inchworm motion. And to do that, it needs to expand and contract its body to grip the inside walls of the pipe.
So the power source is rigid and spins, but the body of the robot needs to be flexible and change length.
Exactly. You can't just connect the motor's spinning shaft directly to the gripper legs. It won't work. You need an intermediary. In this case, they use two. First, a crank slider mechanism, which is a classic intermediary for turning rotation into a pushing and pulling motion.
Like the wheels on an old steam train.
Precisely. But the cleverer part was this second intermediary. To transmit that power from the motor to the legs while the robot's body was stretching and contracting, they used a telescopic shaft.
A shaft that can get longer and shorter, like an old spyglass?
Yes. It acts as the intermediary that faithfully transmits the torque from the motor while accommodating the constantly changing distance between the front and back of the robot. It bridges that dynamic physical gap.
I see. That makes perfect sense. What about a simpler everyday example, maybe for manufacturing?
Bottling plants? Glass bottles are incredibly fragile, especially under sharp impact. The pushers, the metal arms that shove bottles down the assembly line, are typically made of hard steel. Steel on glass at high speed is a recipe for shards.
It's a high impulse impact. It's too fast, too hard.
Right, and basic physics tells us that impulse equals force times time. So to reduce the peak force of the impact and prevent shattering, you need to increase the time over which that impact occurs.
You need to cushion the blow.
You need to cushion the blow. So you add an intermediary, a simple rubber pad or a foam bumper on the face of the steel pusher.
The pillow.
It's the pillow. It absorbs the initial shock, it deforms, and it spreads that impact out over milliseconds instead of microseconds.
Yeah.
The intermediary translates the shove into a push without the shatter.
It seems so obvious when you say it, but I guess the real genius is knowing when to just add an intermediary versus trying to redesign the whole system from scratch.
Sometimes the cheapest, most elegant solution is just a simple shim. And in chemistry, solvents are the ultimate intermediaries.
How so?
If I want to extract a specific oil from a plant, I can't just reach in and pull the oil molecules out. So I introduce an intermediary, a solvent like hexane. The hexane flows through the plant matter and dissolves the oil.
So the solvent's job is to grab the oil.
It's a temporary carrier. I drain off the hexane oil mixture, and then I gently evaporate the hexane, which has a low boiling point, leaving just the pure oil behind. The solvent was just the temporary bridge to get from A to B.
The temporary bridge. I like that. Okay, let's move to section 4. Substitution and replication. This covers principles 26, 27, and 28. First up, principle 26, copying.
Now, copying immediately sounds like cheating or plagiarism, but in TRIZ it has a very specific meaning. It means using a simplified virtual or optical replica instead of the real thing when the real thing is too expensive, too fragile, too dangerous, or simply unavailable.
This is the entire concept of the digital twin.
It is the absolute heart of the digital twin. Why on earth would you crash a $200,000 prototype electric car into a concrete wall if you don't absolutely have to?
Because it's a terrible waste of a beautiful car and a lot of money.
So instead, you build a highly detailed finite element analysis, or FEA, model, a digital copy. You can crash that digital car 10,000 times on a supercomputer from every angle at every speed to perfectly optimize the crumple zones and the battery protection.
And then you only crash the physical car once or twice at the very end for the final certification.
You substituted the physical object with its database copy for 99% of the work.
And I suppose the metaverse fits neatly in here too.
It's a perfect fit. Think about factory planning or architecture. In the old days, to see if your new assembly line layout worked, you might build a full-scale cardboard or wooden mock-up.
Which takes a ton of time and space.
An incredible amount.
Yeah.
Now you build it in a VR environment. You can walk through the copy of the factory, see if the forklifts can make the turns, check if the robotic arms have enough clearance, all before you pour a single yard of concrete.
It's using simulation as a shield against costly real-world mistakes.
And in the world of IT and cloud computing, we just call this virtualization. A server used to be a physical metal box in a cold room.
Right, you had to buy it, rack it, cable it.
Now a server is just a software partition, a copy of a machine's architecture running on a giant hardware cluster somewhere else. You can spin up 50 copies in seconds and delete them when you're done.
The copy is cheap and instantaneous, which leads us perfectly into principle 27. Cheap, short-living objects. This is the disposable principle.
This is all about making a conscious trade-off. You deliberately sacrifice durability and longevity to gain some other more important quality, usually hygiene, convenience, or cost efficiency.
The disposable syringe has to be the most powerful example of this.
It's a world-changing one. In the early 20th century, syringes were made of glass and steel. They were expensive medical assets. You used them, washed them, boiled them, and sharpened the needles.
Which introduces a massive potential failure point. Human error in the sterilization process.
Exactly. And the cost of a single failed cleaning is that a patient gets hepatitis, or worse, HIV. That potential cost is infinite. So we applied Principle 27.
Forget longevity.
Forget it. Make the syringe out of incredibly cheap molded plastic. Engineer it to last for exactly one injection. Then make it physically impossible to use a second time and destroy it.
We optimized the entire system for sterility, not for durability.
We realized that the required life of the object was only about 30 seconds. Anything more than that was not just unnecessary, it was a dangerous liability.
That is a very powerful reframing. Longevity is a liability.
In certain contexts, it absolutely can be.
Okay, let's look at Principle 28, mechanics substitution. This one sounds like we're heading back into sci-fi territory.
It's really just the natural evolution of technology.
Yeah.
We see this pattern everywhere. We almost always progress from a mechanical system, which involves solid parts touching and moving, to a field-based system, which uses something invisible like an optical, acoustic, magnetic, or electronic field.
From solids to fields.
Exactly. Think about your car key. For 100 years, it was a purely mechanical device, a jagged piece of metal designed to physically push a series of pins and tumblers into the correct alignment.
And those mechanical parts wear out. They jam in the cold, they get bent.
Precisely. Now, your key is a fob. It uses an electromagnetic field, a radio signal. The key is a complex cryptographic handshake sent over the air. There is no physical contact with the lock mechanism at all. No wear, no tear.
And sensors follow the same path.
Identical path. A mechanical limit switch on a factory machine has a little arm, a spring, and a physical contact. It clicks. After a million clicks, the spring breaks.
Inevitable failure.
An optical sensor, or a Hall effect sensor, does the same job with a field, a beam of light, or a magnetic field. It detects when an object is present without ever touching it. No contact means no wear, which means a virtually infinite lifespan.
Now, the outline brings up something called homomorphic encryption here under this principle. This feels like a massive leap from car keys and switches.
It is the deep end of the pool, for sure, but stick with me. It is the perfect, albeit abstract, example of mechanics substitution applied to the world of data privacy.
Okay, explain.
Traditionally, encryption works like a physical safe. If you, the data processor, want to read the document or do some math on the numbers inside, you have to unlock the safe. You have to decrypt the data.
You take the papers out, put them on the desk, do your work, and then put them back in and lock it again.
And while those papers are out on the desk, the spy in the corner can take a photo. The mechanical act of processing requires exposure. It's vulnerable.
Got it.
Homomorphic encryption completely changes the paradigm. It substitutes that mechanical need for exposure with a mathematical field. Imagine one of those high-security glove boxes they use in labs for handling dangerous viruses.
Okay, yeah, the big sealed glass box with the heavy rubber gloves built into the side.
Right. You can put your hands into the gloves and manipulate the contents, the data, without ever exposing it to the outside air. Homomorphic encryption allows a computer to perform algebraic operations like addition and multiplication directly on the encrypted data, the ciphertext itself.
Wait a second. You're saying you can do math on the scrambled code without unscrambling it first?
Yes, and the math still works. If I take two numbers that have been homomorphically encrypted and I add their encrypted versions together, the result I get is a new piece of encrypted data. When I finally give that result back to you, the owner of the key, for decryption.
It will be the correct sum of the original two numbers.
Exactly. I was able to process your sensitive financial or medical data without ever seeing the data itself.
That breaks my brain a little bit. You've substituted the physical act of access with a purely mathematical manipulation.
You've substituted the mechanical necessity of decryption with a mathematical field that preserves the structure of the data. It's the ultimate in data security.
That is heavy stuff. Let's maybe lighten things up a little bit with our final section, Section 5, fluidity and flexibility. Principles 29 and 30.
Sounds good.
Principle 29, pneumatics and hydraulics.
This is a very straightforward substitution principle. It simply says, when you can, don't use solid parts for actuation or transmission. Use fluids, either liquids or gases.
And why would you do that?
Because fluids have incredibly useful properties that solids don't. They can flow around corners, they can take the shape of any container, they can transmit force in ways that are difficult for solid rods and gears.
And in the case of hydraulics liquids, they basically don't squish.
Incompressibility. This is the magic behind Pascal's law. If you push on a liquid in a closed system, that pressure is transmitted equally and undiminished in all directions. This allows for incredible force multiplication.
The car brake is the textbook example.
It's the perfect one. You, a relatively weak human, tap a pedal with your foot. That pushes a piston in a master cylinder. The brake fluid, an incompressible liquid, transmits that pressure through narrow tubes to four much larger calipers at the wheels, clamping down on steel discs with thousands of pounds of force.
You could never do that with a mechanical cable. It would stretch or snap. The fluid acts as an invisible, powerful lever.
It's the lever, and it's how the huge flaps on an airplane wing can move against 500-mile-per-hour wind resistance. It's the sheer power density of hydraulics.
And what about pneumatics? That's just using air, right?
Compressed air. And unlike liquid, air is highly compressible. It's bouncy. It acts like a spring. This makes it absolutely perfect for high-speed factory automation.
Why do you want bouncy in a factory?
You want speed and compliance. Let's say a pneumatic arm is designed to slam a box into place on a conveyor belt. The natural air cushion in the system absorbs the final shock. If you used a rigid hydraulic ram, it might just crush the box every time.
Ah, so it has a built-in softness.
It has a built-in softness. Pneumatics are the fast, clean, and somewhat gentle muscles of the modern assembly line.
Clean is a key word there. If an air hose leaks, you just get a hiss of air. If a hydraulic hose leaks.
You get a high-pressure jet of flammable oil, an EPA violation, and a very, very slippery floor.
Good point. Okay, finally, Principle 30, flexible shells and thin films.
This is the move away from heavy, rigid construction. Traditional engineering often says strong equals heavy and thick. TRIZ says, no, strong can also be thin and flexible.
We're seeing this right now in consumer tech with the rise of the foldable phone.
We spent 15 years perfecting the perfectly rigid glass rectangle. And now the cutting edge is moving to flexible OLED substrates and ultra-thin glass. We are substituting the rigid glass slab for a high-tech, multi-layered film that can bend hundreds of thousands of times.
And it completely changes the form factor of the device. You can finally put a tablet-sized screen in your pocket.
And think about packaging. The outline uses the example of bubble wrap.
The single greatest stress reliever known to man.
It absolutely is. But from a structural engineering perspective, it's brilliant. Your problem is you need to protect a heavy, awkwardly shaped object during shipping.
Okay.
You could build a heavy wooden crate around it. That's the rigid solution. It's expensive, heavy, and wasteful. Or you can apply Principle 30. You use a micro-thin plastic film that has been shaped to trap air.
So the air does all the protective work and the thin film just holds the air in the right shape.
Precisely. You use a flexible shell to isolate the object from impact. It conforms perfectly to any shape. It weighs almost nothing. It's an incredibly elegant solution.
And I'm guessing there's a software parallel to rack this all up.
There is, and it actually connects all the way back to our homomorphic encryption example. The outline uses a great metaphor here.
Okay.
Standard encryption is like a rigid shell. It's a vault. You can't see or touch what's inside without opening the door. Homomorphic encryption, on the other hand, is a flexible shell.
Like the bubble wrap.
Like the butter wrap or the glove box. It protects the data inside, but it's malleable. It's flexible enough to let you reshape the data inside, to do the math without ever breaking the seal of security.
That's a really beautiful image to end on. Security that moves with you, that allows you to work, rather than just blocking you.
It's the fundamental difference between a vault door and a hazmat suit. Both provide protection, but only one of them allows you to be productive.
So we have covered a huge amount of ground here. From dental drills, literally outrunning heat,
To self-cleaning ovens and self-healing circuits.
to using the flaw in 3D printing as a feature, to the metaverse as a coffee, and finally to doing math on lock data.
We've gone from atoms to bits and back again, and the same patterns hold true.
So what's the synthesis? If someone is listening to this on their commute home, what is the one big idea they should take away from this batch of principles?
The biggest takeaway, I think, is that the properties of a system are negotiable. We tend to accept the limitations of our materials or situations as fixed. This is slow, this is heavy, this is rigid.
This data is insecure and therefore unusable.
Right, and TRIZ tells us no. If it's rigid, find a way to make it flexible. If it's slow, speed it up so much that you bypass the harmful side effects. If it's mechanical and it keeps breaking, turn it into a non-contact field.
Innovation is often just swapping a problematic property for a beneficial one.
Don't fight the problem head-on. Change the physics of the problem so it's no longer a problem.
So here's our final provocative thought for you. As you go about your day, look at your workflow. Look at the one thing that constantly frustrates you, the one bottleneck.
And ask yourself, are you trying to solve a mechanical problem with a better mechanical solution? A solid problem with a better solid?
What would happen if you substituted a field or a copy or a rush of speed or a flexible shell instead?
It's a good question to sit with.
Friends, thank you for diving deep with us today. A final crucial reminder, this entire exploration was powered by our partners at ID Mechanics 9 on YouTube. Go subscribe. Seriously, if you enjoyed this breakdown, their channel is the source code.
Innovation is a repeatable process. Go learn the system.
We will catch you in the next one. Keep thinking.